saw a proof for W1 hardness of biclic modulo a construction. But unfortunately, the construction which I was trying to describe last time was supposed to be deterministic. But the deterministic construction is extremely hard, and I don't think many of us have background to get into and understand the complete proof. So what I will do today is give you a simple, not so simple, but still understandable complete proof for the randomized construction of this, and that is a very nice gadget. So okay, so let me remind you people what was the NKLH threshold property was, just in case we have forgotten. So let me write it down what we mean. So definition, okay. So what was this definition of NK low high NKLH threshold property, okay. So what we said, for NKLH in natural numbers with high being more than low, a bipartite graph T equal to A union B comma ET with a partition A Vn satisfies the NKLH threshold property if the following two condition holds. What was the first condition, which we called T1? For all x in AK plus 1, means you take any k plus 1 size subset of this, then is greater than equal, no, it is low. So it is L, at most L. And what to be said, T2, for all x indices of k, for all x, right, or for all, let us say, I1, I2, Ik element of what? This. There exists Vi1, okay, there exists Vi1 in capital Vi1, little Vik in capital Vik, okay, such that x equal to Vi1, Vik. What is the property? If you look at the gamma x, it is at least high. So basically what it tells us that given any k index from this, I will be able to find a vertex each in each of the part corresponding to this indices, so that if I look at the common neighborhood of them, then that is at least h, right. So these are the NKLH threshold property we were interested in, and what is the prime objective of today, first objective of today is to, what I would like to give is, this is a lemma which is what I want to prove today, okay. So what I want to prove, that for KLN H in N positive, okay, with N greater than equal to max of whatever the max is, two k plus 1 square, and 20 for with n greater than equal to this, L equal to 2k square plus 4k minus 1, and as always low is less than equal to high, and high is less than equal to n to the power 1 divided by 4 into k plus 1, Okay, one can construct in time polynomial in n a random bipartite graph, a bipartite random graph satisfying the n k l h threshold property with probability at least 9/10. Okay, this is what it is. Now this is a randomized statement. Okay, so now if you recall, we had a construction. Remember, we had a reduction, right? So let's just look at this. So this is the reduction lemma which we had. Remember what we did for the reduction. So if you had this kind of property, right, in the reduction, then given a graph g comma k, okay, we applied a threshold graph with some n k l h property and constructed a bipartite graph h which was L disjoint union R comma E, right. So given a threshold graph, we constructed such a graph. This is a part of the condition.
Is that 1 by 4 into k plus 1?
Yes. It is n to the power 1.
Okay.
It is
actually 1 by 4 into k plus 1.
It is like this, like 1 by x, where x is n to the power 1 by x, where x is like, okay. So this is what we constructed, right? And what was this construction? Basically this construction was, we took this, so let's call this a, b, comma, et, this threshold bipartite graph. And how did we say it? We said, hey, let's look at pair, right? We basically considered a cross a here, and b was b. So this was this was our L star in the beginning, right? And how did we give edge? So notice that every threshold bipartite graph, there is a bipartition v1, v2, vn. So here a also is it's partitioned into some v1 to vn, right? No, I shouldn't say this is a cross a. So for every pair, how did we give edge? We said, hey, look, if this vertex is adjacent to this guy, represents some u comma v. If this guy is neighbor to both u and v, then you put an edge, right? So this is what we did. And finally, how did we got L star to L? We said, okay, look at your E of g. If some tuple does not appears in E of g, then just delete that vertex. So basically, you can think of this, whatever this L is, basically is isomorphic to E of g. Basically, I am not saying it's completely correct because each v1 has a big size, right? But only those tuples survives for which there is a corresponding edge. So for example, how did we define this? We said, okay, we have a map from T E to V of G, right? And how did this map work? We said, hey, the property is that for all I comma j in Vi, tau of I is equal to tau of, for all I comma j in Vi, no, we shouldn't say this, Vj, for all in Vi, tau of Vi equal to tau of Vj. So basically every color class mapped to a single vertex, right? So this is why we had n color classes, and each color class is mapped to a single vertex in Vg, right? So how did we say? We said, hey, look, if there is a pair here such that there is a corresponding, so if I look at a pair here, I can go back to with this map, I can go to V of g. Now I look at that, that's also the pair, right? Because think of this Vg is equal to some 1 to n, vertex set is 1 to n. So if there is an edge in the graph, I left that vertex, otherwise I deleted this vertex. And what was the property we proved? We proved for this property h1 and h2. What was the property h1 and h2? If G contains k clique, then there exists a set X in L choose S. I will tell you what S is. S was be fixed to be K choose 2. X in L choose S. If G contains a K clique, then there exists a set X in L choose S such that its neighborhood in H of this set X was how much? Greater than or equal to high. Or
n to the power
what?
n to the power of 6 by k plus 1.
No, not in this theorem. When we sub, okay, and H, this is a reduction lemma, okay, and what was H2? If we said that if G contains no K clique, if G contains no K clique, then for all X in L choose S, what was the property? Is less than or equal to L, right? This is what we used. Okay. Now, I gave you proof for H1, but I did not give you a proof for H2. I hope you have worked out. If not, here's a very simple idea. So, what I want to say, if G contains no K clique, so if
Just to clarify one more time that tau h of x, that is neighborhood of x in the graph H.
it's not neighborhood, it's an intersection of neighborhoods.
Intersection of neighborhood. Okay.
Otherwise, I would have written N. Okay, it's a common neighbors. Okay, so if G contains no K clique, suppose this is the assumption, G contains no K clique. Okay, okay, and without, suppose for contradiction, there exists L, there exists say X in L choose S such that if I look at the common neighborhood of X is at least L plus 1. I am going to show this. If this happens, then I will get you a K clique in G. Okay. So the proof idea is very basic and very simple. Look at your L. Look at your L. And look at your right, which is actually equal to B. Okay. And now I have X in L choose S. So here it is my X. Here's my X. Okay. Let's W be equal to V of X. Means all those endpoints which are here. Okay. 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 So first of all, now we will go back to my threshold graph T. So I have this L and R, this is my H, and my threshold graph is here A and B. Okay. Now I want to look at W here. Okay. What can be the size of W? One thing we definitely know is tau H of X, whatever this set is, right, whatever this set is, this is contained inside tau T of W. Right? Why? Look, when you look at X, the guy which is in a common neighborhood here, it is common neighborhood with respect to pairs here. So they are also common neighborhood with respect to everybody here, right? And that's just this much. So this is the property. Now what can you say about W? So what is the size of tau T of W? This number is at least L plus 1, at least L plus 1, because this size by my definition is greater than or equal to L plus 1. Now, so what is the size of W then? It's a threshold graph. If I have neighbor more than L plus 1, what is my size? What is my size? Its size is upper bounded by K. Look, what is the threshold graph property tells us? Look, is more than H, right? But what does it says? If I have a set of size K plus 1, its neighborhood can only be at most L, right? So if I have an object of size L plus 1, all I can say the size of W is strictly less than or equal to K. It cannot be K plus 1, and this is all that I am saying. So W is less than or equal to K. This is all that I am saying. But what was W? W was the union of pairs. How did I construct W? W was nothing but the endpoints of these X edges. But what is the size of X? Size of X is exactly equal to K choose 2. Right? What does it mean? It means size of W is exactly equal to K. Otherwise, you cannot get K choose 2. If size of W would have been say less than or equal to K minus 1, you cannot get, even if you take both tuple, you cannot get a set of size K choose 2. Right? What was W? W by definition was endpoints of every object here, and every object here is a 2 tuple of some set. Right? So this implies that this is exactly equal to K choose 2. Right? And then what does this implies? W has size K, it has all K choose tuple. Now if the very fact that this pair belongs to L, it means there is an edge between them. It means you have got a clique over W, and that's a contradiction. Okay, I mean you can make this argument yourself. This is not, I just gave you a flavor because I didn't do last time and I expected you not to do, so I went through. Okay, fine, but that is all that my objective was, that even the H2, showing H2 property is not hard. Okay, so I start for a contradiction, I start with an X of size K choose 2 with neighborhood L plus 1. I look at the vertices involved in this, I go back to my threshold graph and I say, hey, since the common intersection is larger than my threshold, certain threshold, the set size which is the intersection, it cannot be more than K. Well, but then if it is not more than K, it is upper bounded by K. Then if it is strictly less than K, then both tuples, then the size of X cannot be equal to K choose 2. So the size of W is exactly equal to K. It means every pair is present, but if every pair is present in L, only if the corresponding guys has an edge in my original graph, which means that I have a clique in my original graph, right? So this is the threshold property which we showed H1 and H2. Now this was a deterministic proof, but now since we will apply, and then what were, like, so this threshold graph, if I give, which happens with some random probability, right, this threshold graph satisfies this property with probability 9 over 10, then I will satisfy H1 and H2 with probability 9 over 10, because in this construction I do not do, you gave me the threshold graph and I just do deterministic construction, I do not lose any property in this construction once I gave you T, right. So all I will say is that blah, then this H satisfies H1 and H2 with probability at least 9 over 10. Okay, okay. So once we had this reduction, we had a third main theorem, and let me rub this. Okay, I am giving you full proof so that after that I can just concentrate on that. Once we had this construction, we had the following nice So using this lemma, this reduction, okay, we can prove the following theorem. What was the following theorem? Given a graph G and a positive integer k, with n at least max of whatever this number is, okay, one can construct a bipartite graph H L R E in polynomial time such that, here is my soundness. What was my soundness? If G contains k click, then with probability 9/10 there exists x in L choose S, okay, and S will be as always k choose 2, okay, this is the same S, okay. There exists x in L choose S with such that if I look at of this guy, how much it is? So look, I am going to apply this lemma with my construction. So I am going to apply this construction in this lemma. So my parameter will be n, k, and what will be my parameter for L? L will be whatever this number is, right? 2k square minus, oh no, plus 4k minus 1, and what is my high? I will apply with this, okay. So what I say, okay, is n to the power 1 divided by 4k plus 1, and what is completeness? Completeness is if G contains no click, contains no k click, then with probability 9/10 for all x in L choose S, what will happen? Is less than equal to whatever that number is. What did you apply with? Here, L is 2k square plus 4k minus 1, fine, okay. So this is what we can prove, okay, this is what I can prove. And how did we prove such a theorem last time? Well, nothing, right? We took our graph G, right, and we applied the reduction lemma with the appropriate threshold graph, right. So now that we have a construction of this with probability 9/10, so given G comma k, you apply this reduction lemma with the threshold graph with property what? N k, what is this? 2k square plus 4k minus 1 and n to the power 1/4 into k plus 1. This is it, and then you will get an H. So what do I feed here to this reduction algorithm? I feed my graph G comma k.
Just one thing, in this, for the soundness, the probability both are exactly 9/10?
Yes.
Okay.
We will see how it comes. Yeah, okay. We can fail in both cases, okay. So I will give you a graph which satisfies both probability with probability at least 9/10. At least 9/10, and hence both soundness and completeness will happen with probability at least 9/10, okay. So it just depends on this, right? Like it's a graph which satisfies this threshold property with probability 9/10. Once, because we are not doing any randomization in the reduction, right? Once I gave you the graph, the construction of this graph is like really deterministic polynomial time. Once I gave you the threshold graph, and then all the properties are predetermined once G and the threshold graph gets fixed. Now whether this has this property depends on whether that property is satisfied with the threshold graph or not, because you are doing nothing in this construction. Okay, so if you apply this construction, you will get this theorem, and once you get this theorem, what will you show? You can show that at least now you can show at least that bi-click does not have or randomized FPT algorithm. Or how do we say this theorem? With probability 9/10, how will we say this statement? I mean, no, it's not a deterministic, like, because I cannot construct this in, like, so my algorithm is randomized polynomial time, so it can fail this. So how do we show? What should be the statement of the theorem?
Now, suppose the bi-click is outputted with
I think the right way will be say there is no randomized. We will try to figure out what should be the right statement here. Okay, there is no randomized FPT algorithm for bi-click. Okay, for now let's stick with this. We will try to formulate it. What should be the correct statement in this situation will be, okay, and we will try to put that in the notes. But for now, there is no randomized FPT algorithm for bi-click. And how will we prove this? Oh, this is very easy. You given a graph G comma K, I apply my construction, and I, yes.
Why will we get that? I mean, yeah, we have to get that from W1 hardness of click.
Yes.
He's going to prove that.
That's what I'm going to.
He's just going to get.
No, yeah, I mean, even if we have this reduction, just a second. Suppose we have this algorithm. Suppose you give this reduction and we have this algorithm.
Yes.
So we should be contradicting the fact that we should be getting it, if we have this, we should be getting an FPT algorithm.
For randomized FPT algorithm.
Okay.
Yes.
Deterministic FPT algorithm.
No, we cannot, right? Because I might, if I had a randomized, look, this reduction is randomized, right? Right. So this reduction is randomized, right? Because when I construct an instance of this is a randomized instance. So even if I had a deterministic algorithm, right? Even if I had a deterministic algorithm here for this particular problem, right? I cannot be so sure that the instance which I have created had this beautiful property, right? Had this beautiful gap property that given an answer here, I can lift an answer here.
But so basically we are contradicting the fact that click has a randomized FPT algorithm. This is what we're contradicting.
Yes.
And this is also
Yes.
unlikely.
Yes, unlikely. Yeah. We believe randomized ETH, we believe randomized W1 hardness, everything. Okay? But as I told you, there is a deterministic construction which shows this. But it's just that, so you are right completely. All we will be able to say that basically we are basing on the assumption that click cannot even have a randomized fixed parameter tractable algorithm. Yes, you are right. That is the assumption we are going to assume.
Randomized with constant probability.
Whenever you talk about randomized, it is always with a constant probability. Right? That is why whenever we make an FPT algorithm, we incur a failure of 1 over f of k, then we boost it by repeating it several times or by applying some other technique. So whenever in randomized algorithm talk, it is always with a fixed constant probability of success. Okay? And so what is the reduction? Reduction is as I gave you that day, right? So I construct my L graph, I construct my L union R graph using this threshold graph. So I have constructed this graph, and now what do I set? I set my t equal to remember what did I set? I used to set t equal to this threshold. So what is the threshold here? 2k square plus 4k minus 1. So I was adding plus 1. So I will just use plus 1, then it just, so t is this. So now I am saying this guy G has k click if and only if, and I will do some more thing, if and only if H star has k t comma t. And what is this t here? You just add here t minus s vertices, t minus s, where s is k choose 2, and make it adjacent to everybody in R, and that's all that I'm saying, right? So now if G has a k click, then I know that I have a S size object in L with certain amount of neighbors, right? As many neighbors as high, right? As many neighbors as high, but high is at least L plus 1. High is at least L plus 1, right? So low, so at least it has 2k square plus 4k neighbors, right? L, I set L equal to 2k square minus 4k, 2k square plus 4k minus 1, right? Now what is high? Is at least one integer larger than this, right? And this is exactly what I said, 2k square plus 4k. So if G has a k click, then I can find a set X with the property of size k choose 2 that has at least these many neighbors. Now I take this guy which is common to everybody, and then I get k t t, right? So this is the forward direction. Like there's nothing backward direction. What we have to show, if G does not have a k click, then I cannot find such a structure, right? So we start as always. So this is why we proved, suppose G does not have a k click and we do have a k t t. So if I do have a k t t, it means this guy can only provide t minus s guys, but this guy has to provide how much?
S guys.
S guys, right? So but what is the property of this s guys? If so, it shows that S has Blah number of this
Because of the H2.
because of the second completeness property,
Completeness, okay.
right? But we know that this guy has at most these many neighbors here. That contradicts, right? Look, what does it say? Look at this S. Look, you can only take t minus s guys from here, right? S guy, at least S guy has to come from here, at least. So, but what do we say? Just forget about at least S guy, choose the S guy with the highest common intersection for all that you care. But even those guys, if I choose, how many common neighbors they have? Here. Minus 1, right? But you are looking for so much of neighbors. So this is where, and you had a question last time that why are we using this threshold graph? They are gadgets, right? What? So this is nothing but a gadget, right? It's like generally we build gadget with small things. Here the gadget is like a big gadget. For every n vertex I have a big gadget which we modify to suit our needs. So what is our gadget? T is our gadget, and we modify it to suit our needs. But in particular what we do, we make a small thing, but we always create certain threshold, certain gap between them, right? But we are able to construct that from a small building blocks, and we make it big because the size of the graph is still, but we say, hey, here's the 3 guys. So for example, when you give a reduction from say SAT to vertex cover, you have this matching edges, and then so what is the property of this? If this is satisfiable, you will at least take these many vertices from the solution. If it is not, then this, right? But the good thing is the threshold property graph you can construct from just cycle and matching, so you can see this. These kind of objects we are not able to see it, so we say, hey, if given an n, I get this n vertex graph, and we are done. Okay, fine. So I hope I have explained to you, and what remains to show is that lemma. Okay, and hopefully in next 45 minutes we should be able to prove that. Okay, okay. So I'm going to rub everything and just leave this on the board. Okay, and I will leave the last one and leave this. So it was basically, I wanted to repeat this for your purposes in terms of randomization. Yes, this is not required. Nothing is required. Okay, so wear your hat if you have attended my MFCS course, because we are going to get, if we are, I hope we can get some intuition from there. Otherwise, life is going to be slightly difficult. Okay, so how are we going to construct this graph? Well, this is very easy. The construction of this graph is very easy. Here's my construction. I'm going to take side A, side B. Okay, what is the side of A is equal to B equal to n square. N square. Okay, and I have told you a probability P. We'll fix those. I look at this edge with probability P, I put an edge. Okay, so how do I construct my graph? I construct my graph as follows. In one side I put n square vertices, in B I put another n square vertices, and for every pair I put an edge with probability P, which we will fix later. Okay, so this construct my graph AB, but it does not give you a partition, right? I also need to give you a partition, like what does it demand, right? I have to give you partition V1 to V2 to Vn, right? I have to give you this partition. Oh, that doesn't matter. I can think of A as vertices from 1 to n, n plus 1 to n square. I just give them name. First n guy is your V1, n plus 1 to 2n guys is V2, and so on and so forth. So I have given you a complete construction of the graph, and clearly you can construct this graph in polynomial time. I take n square vertices, I take n square vertices for, and I will define what is my probability P of n will be. It will depend on n. Okay, so that's my end of the construction. Okay, and now I want to show, first of all, let's try to understand what it even means that this graph satisfies property T1 and T2. Given that n is this, L is this, blah blah, what does it mean that it satisfies this property, right? What is that P of n is? Okay, so to do probability, first of all, let's understand what is my sample space. What is my sample space? What is my omega? What is my omega?
We are putting an edge with probability P between a vertex in A and a vertex in B.
So what is an omega? Omega is a sample space. So I give you a random experiment, right? Given a random experiment, omega is set of all objects which we can obtain by this random experiment. So now my question is, what all things can I get in omega?
All pair of that is one from A and one from B. Yeah, the full bipartite graph.
Every possible bipartite graph on n cross, like every possible bipartite graph you can think, right? Because with certain probability, right? So basically this is all, and this is important, this is very important, that my objects are of this omega are all bipartite graphs on n and n objects. So n square and n square object, right? So this is very important to understand. Okay, some G M, let's not Q, some G is Q, some number where basically, so it's every possible bipartite graph. Now let's fix each of some particular GI or G V comma E. What is the probability? So now I have defined you an omega. Now I need to define your probability distribution over this. How am I going to define a probability distribution over this? Okay, so here is my way of defining a probability distribution, right? I have to define a probability distribution. So probability, I'm going to define on particular graph some G, is that okay? So it has
G1 that is, or
some G, it doesn't matter, it's in omega.
the V and D of the
It doesn't matter, right? V is this, A comma B and this. So now you have some subset of edges, right? Basically you have a graph like this, and some edges are present and some edges are not present in this graph, right? Some edges are present. Okay, for simplicity I am going to write P of n by just little p. Okay, I do not want to carry this notation all over. So if I have this, look at the edges which are there in this graph. They are put there with probability what? P. So it is like P to the power cardinality of E. And other guys are not put with probability 1 minus P n square minus E, because there are, sorry, n4. In our case it will be n4 because there are n4 pairs, and this is it. So this defines the distribution over this omega. So now I have told you what my space are, I have told you what my elements are, right? Now when I say that, so people call this what is called Erdős-Renyi model of generating a random graph, okay? So when you say that, and this is denoted by actually some curly bracket G and P is like n vertices and P is the probability of by which you give. So what we constructed is a specific kind of family of bipartite graph. We had n square vertices in one side and P in one side, okay? But I will denote this by G and P, it does not matter, because by this we mean this, okay? But when you say that this graph satisfies this property, what do you mean? What are you looking for? G and P satisfies this property P. I want to say that G and P, this is how I have created, G and P satisfies a property P with probability blah. What do you mean by this? Right? Some probability, say property pi with probability something. What is the meaning of this line? Let us first understand this. What is this event we are trying to capture? So basically it is nothing but, let us call it event. What is the event? G in omega, G satisfies pi. This is my event. So when you say that G and P satisfy property pi, basically you mean probability of this event, right? G in omega, G satisfies pi, right? And since, yes?
Defining it as a set, wouldn't that probability equal to cardinality of event divided by cardinality of my event?
No, each element in G has a different probability. I have defined my distribution already. It's a finite distribution, like it's a finite, it's like finite domain, right? It's not uniform, that not everybody is getting uniform probability, right? So it could be that the different graph in my event has a different probability. Look, every element, look, I have defined a distribution, each Gi I look at edge and this is the probability of this guy, right? Why can't I have an event 1, 2, 3, 4, 5, this is half and rest is like 4 half by 4, 1 by 8, 1 by 8, 1 by 8, 1 by 8. But if I give you 1, 2, then what is the probability of event 1, 2 is half plus 1 by 8, right? Probability of 2, 3 is 1 by 8 plus 1 by 8. Right. So once I have given you this omega, I have told you what is the probability of each elements are. It's a finite, it's not an infinite family, it's a finite family. So basically I have told you the basic objects here. So now event of this is nothing but, you are right, it is nothing but summation over G in event probability of G, because I have told you what is the probability of G means. So I can just sum them over them, okay. So in our case, what are we supposed to show? I want to show that G and P satisfies property T1 and T2 with good probability, with probability 9 over 10. So first of all I have to say what my P is, so in random graphs you are always allowed to have this P, okay. Now there are two questions to understand. Why are we trying to show this? Look, first of all, how do I even know that such a threshold graphs exist? I mean, I cannot even construct a bipartite graph, right? But if I show that G and P happens with non-zero probability, what is the meaning of this? It means this event, so this set of objects is non-empty, otherwise it cannot have a non-zero probability, right? It means if this is non-empty, it means there are bipartite graphs which satisfy this property, right? But if this is 0, it means there is absolutely no graph. But it's my job to define my probability distribution. I can define it with respect to any distribution. So that is a handle which you have got. Right? Right? So this is what. So basically, if I change P for the same object, my distribution will be changing. If I put P equal to half, I have a different distribution on GIs. If I put P equal to 1/4, I have a different distribution on the same. Like my omega remains the same, but my distribution keeps changing based on what P I choose, and that is a handle you have. So every time what you do, you do your computation, you get set of equations, and you say that okay, if this is the event which I want, and I want this event to have a non-zero, then you trace back and fix the probability accordingly, and this is how you do. Okay? Okay, so this is what we would like to do. Okay. Is the overall idea clear? Because this is the end of the construction. Like as an algorithm, this is what I will do in an algorithm. I will have n square vertices here, n square vertices here, and with some fixed probability for every pair I will put an edge. But I will say that this is a great object because this object itself satisfies this property. Because if I have chosen this, because this happens, because I would have found an object of this event set with probability 9/10. That's it. Okay. Okay, so I hope after this there is less science and there is a more of maths, like more of computation. I wouldn't say even science. Okay. Okay. So but I will do this for you. Okay. Okay, but is the overall idea clear? What you would like to this? Okay. Okay. For some practical reason, some things are set. Okay. So you know what is set. L is 2k square plus 4k minus 1. Okay. And I want this to be h, whatever is less than equal to, and p which depends on n, right, it's set so that the maths goes through. Let me write down here n minus, what is this number, minus 2 k plus L plus 3 divided by okay. Okay. So to prove that our event happens, what are we interested in? We are interested in the event that G satisfies property T1 and T2. Okay. So I want to prove first G and P does not satisfy property T1, and then I will prove G and P does not satisfy property T2 with probability say 1 over n square, and it does not satisfy probability 1 so with if I show this, we are done. If I show that G and P does not satisfy property T1 with this and T2 with this, then we will be done. Why? So let's look at that. Why, if we are able to prove this, we will be done. So what is the probability that G and P does not satisfy T1 or T2? What is this? Apply union bound.
At most 1 1 by n square plus
1 over n, right, which is less than or equal to 1 over 10. You can choose your n accordingly, that this is n is large enough that this is this, right? Agreed? Does not satisfy T1 or T2 is 1 over 10 because by union bound. Is it okay? You look very confused.
Single lower bound that you said. There's at least 20 anyway.
Yeah, so like you said 100 for all that you care if the maths doesn't go through. Okay? These are not important point. The point is, if I show this, I show this, I will be able to show this, and this is like it's like n is a growing number, so you can choose whatever you wish to make this as much as small as you wish.
So for example, as you said, when we're giving randomized these things, you want probabilities to be constant.
Yes.
So I mean, here basically a probability is 1 by polynomial in n. We're just saying
No.
just one.
This is a no. This is a failure probability.
okay.
Yeah.
So success probability is at least 9 over 10. It does not satisfy this property.
True. But okay, if I didn't upper bound it by 1 over 10.
Okay.
I just keep it 1 by n squared plus 1 by n.
Yes.
And then the probability that it will satisfy will be 1 minus this,
Yes.
which is some function of n.
No. For any n greater than or equal to 1, I can say that it is at least constant.
But can you do this always? For example,
If you cannot do it, then that's not a proper algorithm.
so basically I'm saying when you're constructing randomized algorithms,
Yes.
and if I just give you a failure probability of 1 by polynomial, say,
Yes.
or even 1 by exponential.
Yes. Then I succeed even with more than constant.
Then why do? Okay.
But it's not always possible that maybe my failure probability was close to 0, sorry, close to 1. Then I cannot say anything. If I was able to show, all I was able to show here that, oh, I failed with probability 1 minus 1 by say 2 power n. Then this is not an algorithm which I can utilize. If I can, all I can, so I can upper bound my bad events with 1 minus 1 by 2 power n. But if I can bound this by this, oh, I am great then, because then I succeed with 1 minus 1 by 2 power n. Even for n equal to 1, I am great.
Okay, just to clarify one thing, GNP does not satisfy probability 1 with probability exactly 1 by n square or at most?
At most.
Okay, at most. For both of them, it is at most.
Yes. Does it matter? Think about it.
Not at least. That is
That's all that matters, right? Exactly.
initially, I thought it to be at least, but maybe later realize it's wrong.
Exactly. That's great. Okay. Okay. So this is what we would like to show, and then we will be happy. Okay. So first one is really obvious. What is the meaning of this? What is the meaning? GNP does not satisfy property T1. What is the meaning of this? What was T1? For all x, this is less than or equal to L, right? It does not satisfy means some x which are at least greater than or equal to L plus 1 neighbors. That's it. Okay. So, proof, let x be the number of k plus 1 comma L plus 1 subgraphs in GNP. So basically, what are you doing? Your event is all those graphs be the number of this subgraphs in this, right? So basically, so what, you have to show this. So let x be the number of subgraphs in GNP. Okay. Okay. So now you might be confused. What is x means then? Number of k subgraph. No, I am thinking of x as a random variable which takes an omega, it gives a function r, and what is omega? Is a graph. And what is x of g? It is the cardinality of k, k plus 1, l plus 1 subgraph in G. This is what it is. Okay. So what is, this is what it is, but this I can write down as pair A prime B prime, right. A prime is a subset of A, k plus 1, B prime is a subset of element, right, and B prime is contained inside tau z of A prime, agreed, and this is exactly the same thing, it's same, like this number is nothing but, I can just count this tuple, right. So what will be an expectation of x comma g?
Should it not be just this number multiplied by 1 by multiplied by p to the number of edges in?
Yeah, so I am asking, right, what is an expectation of x? I told you what x of g is.
It's n squared cubes k plus 1 times n squared cube l plus 1 multiplied by e
The
to
probability of that, that's it. Right, basically what is this? It's a tuple,
k plus 1 from A and l plus 1 from B.
yes, but right now how, what all graphs will have, you have to also distribute it over, so whatever this is and the remaining guys could be anything, I don't care, right. I fix this, then I can just go over anything, no. What is this xg is this, so when I fix a set A and the set B, right, some numbers, right, so what is, so how, what did I write, this is nothing but A prime in this and this, right. So for a particular x, particular g, there is some number, but we are not interested in this, we are interested in expectation of x, which is nothing but summation of xg.
Into probability that G happens.
Not g happens, what, this is just a function x of g, right, but it is a number which it takes, right. So what is the probability that x of g, or not x of g, that is a wrong way to say, what is the probability that x is equal to say 100, right, because these are just numbers, right. So what is these numbers? So basically it is mapping, so it takes a graph G, it maps how many k plus 1 L plus 1 subgraph. So basically these are numbers here. Now when you say what is an expectation of x, it is this number into probability of happening of that object, right. So another way of looking at it is that I fix A prime here and B prime here and say, okay, what is the probability? So like I want to sum over everything. So what is the probability that this happens, right? And I go over all possible things. So expectation of x, right? Because I can write this as nothing but this, right? I can also, so think of this way, that I fix a tuple A prime B prime and look at the probability of this with respect to all possible graphs, right? So like what, so if I fix A prime B prime here, so what is an event A prime B prime? Like suppose if I write A prime B prime, so this is basically, it will mean all those graph G such that there is a clique K A prime B prime, right. So when I say A prime B prime, it is a probability of these all objects, right. So when I write just A prime B prime, right. So now, but when I am doing this, like so this is a number which is coming, right. When I put this graph, I am getting some numbers, right. Or the other way to look at, okay, so this is A prime B prime, how many people achieve this, and just sum their probability, it's the same thing. Yes, so it will be counted in those different A prime B prime, right. Right. So if I sum over every A prime B prime and I count this probability, so what is it? What is that? This is cardinality is 100. So xg, let's write it as a set. You can also think of this way, cardinality of this. So or another way of thinking of this, when I say xg, let's look at the tuples which it contributes. Right. This is the tuple which contributes. Suppose these are the tuples which gives me k plus 1 L plus 1. I write down the tuple A prime B prime for this graph, fixed graph G, I write down tuples here. What is the probability of this tuple? Is whatever this object is, this, so you sum them up, which is same as I take this and I multiply with the event of the probability, and that's it. So as Arindam was saying, just this is nothing but n square, choose k plus 1, n square choose L plus 1, and p to the power k plus 1 times L plus 1, because you want edge between all k plus 1 and L plus 1 object, and this is it, right. So this is nothing but less than equal to n power right. Is this correct?
But should it not be p to the power of? So I already fixed the clique to be k a prime comma b prime. I know that there is a y clique over a prime and b prime.
Yeah.
All these edges are already fixed.
What? So they're not just the probability that those edges are present is what is.
What I multiplied with.
That p power that thing.
Yes.
Oh, the probability that
These edges are there, right? No, I thought that this is the easier part. Okay, fine. To the power p to the power this. So what is p? We said somewhere, no? This, right? So if I took this, k plus 1, L plus 1 will die out, and then what I will get is n power minus 2 times
2 into n plus k plus 3.
plus 3, and this is lies n minus 2. They have been chosen appropriately to give whatever you feel like, but this is expectation. Probability x is greater than 0 by Markov is what? By some a square, but there is no So this is less than equal to this. This is Markov. Come on, guys. This is Markov. Everybody looks very. You don't know Markov's inequality? I mean, you shouldn't do theoretical computer science. You should do something else in life then. Haven't done any course in probability? This is the most basic tail inequality. Okay. I am not going to prove this. Okay. That's it.
Just a minute. Why is that? Okay, n. Okay, so Pn is equal to n power minus. Okay, so there are two minuses. So one is there is something.
What happened to you?
So what is Pn? So is that minus actually that?
Oh, there is no minus here. Sorry. Okay, you're right. Yeah, it is 1 by n to the power something. Okay. So probability that GNP does not satisfy T1 probability that GNP does not satisfy T1 is less than equal to probability that x is greater than 0. If x is greater than 0, it means there is some graph right. What is the probability x greater than 0? It means it basically counts probability over all those objects where you have this kind of thing. This is n minus 2, right. So I have bounded the probability that when I start giving this family, these graphs, then look at the objects, look at the graphs which do not satisfy property T1, they are bound, their mass is bounded by 1 over n square. This is what exactly it means. It means nothing more, right. Basically what is this probability? So you look at those event where which does not, which has a k plus 1 size subset and has an L plus 1 size subset and they have a biclick. Look at those graphs. What we have been able to bound, probability of that event is at most n square, n to the power minus 2. See, what was my x? What was my x? It was, so if you think in a rationally, xg is something, right. So what is this? So what, look, if I put, say, what is this number, some 1 to these numbers, how many such, what is the value x can take? It can take 1, 2, 3, blah blah blah, up to any bipartite graph can have, say, complete bipartite graph, it could have as many subgraphs, right. So all these numbers it will take. So when I take 1, which all graphs has exactly 1 kk plus 1 and L plus 1, so I write down those guys, probability of that. Then 2, all those graphs which has exactly 2 objects. 3, all those graphs which has this, right. So when I do probability that x is greater than 0, probability, it is same as say is equal to probability that x is equal to 1 plus probability that x equal to 2, probability x equal to 3, and I sum them up, which is nothing but I take this union of all those graphs where I have a k plus 1 and L plus 1, but I had subdivided them into parts. Okay, these graphs has exactly 1, 2, 3 up to that number, right. So this is the world we are working in, and what I have done now that, okay, here is my, there could be many graphs. I am not saying that there are not too many, there could be exponentially many graphs here, there could be exponentially many graphs here, but all I am saying to you that look at the mass of them, look at the probability of them, it is at most 1 over the square. These are the people who do not satisfy this property. So now from now onwards we will not worry about these guys, we will only worry about these set of people.
The graphs that doesn't satisfy this property.
T1.
The right hand side. The graphs for which
there is a set of size k plus 1 which has a neighbors which like those graphs which has a complete bipartite subgraph of size k plus 1 L plus 1. Probability over those graphs is bounded by 1 over n square. This is what we proved. Right? I am never saying that the number of graphs here is small. All I am saying to you is that the mass of the probability over these objects is small. Okay? Okay. Okay, so we are done with the T1 property. It's like 15:20. There's a lecture at 3:30 about women something which lots of people want to go. How many of you want to go? Okay, so Venkatesh seems to be the only person who wants to go. I also want to go. This is the truth, but I would like to finish this because otherwise it will become too much of a mess, starting all over again next day. So maybe it's a good time that we can take 10 minutes break and come back after coffee, because then I can start proving T2. Like it's not much, it might take another half an hour, 40 minutes, I really don't know, but it is just about going through the motion and doing the computation. Okay, can we just break for 10 minutes?